What is the most fundamental, most unifying principle in science? The answer to this question, many scientists would say, is symmetry. The laws of motion, for example, are the same wherever you are and whenever you make an observation. If they weren't, observations would not be predictable and experiments would not be repeatable. The idea of symmetry and a universal tool for the unification of mathematics lie at the heart of the work of Sun Binyong and the remarkable contributions he has made to the representation theory of Lie groups. In pure mathematics, a group can be defined as a set of symmetries of an object. For an equilateral triangle, for example, flipping it around its vertical axis is one symmetry, as is revolving it through 120 degrees. So is combining these two operations. The French mathematician Évariste Galois used this thinking with great success to solve problems of polynomial equations in the early 19th century. It wasn't long before mathematicians found they could apply this theory of groups to other fields. Later, in the 19th century, the Norwegian mathematician Sophus Lie used group theory to study the continuous symmetries of differential equations by investigating groups that were also manifolds. The concept of a manifold, which is the generalization of a surface in space, is of central importance in the field of differential geometry. Lie did not succeed in developing a unified theory of differential equations. However, the Lie groups he developed were soon found to be of great use in almost every other branch of mathematics.
Group is a fundamental concept in algebra, and the manifold is a fundamental concept in geometry. So Lie group is just a combination of these two. Some key symmetries in physics, such as space-time symmetries, exist in continuous family. So Lie groups provide perfect mathematical framework to present these symmetries. I use Lie group in number theory.
The study of Lie groups became a hot topic once mathematicians realized their power. Today, they are being fruitfully applied to a spectrum of sciences that includes engineering, computer science, particle physics, and economics. Since the early 2000s, Sun Binyong has made 3 important breakthroughs in the field.
My research focuses on representations of classical groups and their applications to L functions. These 3 results, along with subsequent work, will advance the study of L functions. Lie group representation theory originates from quantum mechanics. These studies may also impact further quantum physics research.
In addition to their expanding applications, Lie groups have emerged as the central discipline in a grand project to unify mathematics called the Langlands Program, proposed by the Canadian mathematician Robert Langlands in 1967.
Robert Langlands observed that the properties of L functions are related to the properties of other types of functions, known as automorphic forms. This observation led him to propose the Langlands program. Langlands program aims to establish connections between number theory and the representation theory, with L functions serving as a bridge between two fields.
Without a doubt, Sun Binyong is China's leading figure in Langlands program. For his remarkable contributions to the representation theory of Lie groups, the 2024 Future Science Prize in Mathematics and Computer Science goes to Sun Binyong.